Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. In this lecture, we will study about integrating factor. Before this lecture, I have recorded one video based on integrating factor. Integrating factor. What is integrating factor? Sometimes we have a non-exact differential equation. To make it an exact differential equation, we need a multiplying factor, which is called integrating factor. If we multiply the non-exact differential equation by integrating factor, it will become an exact differential equation. The integrating factor is sometimes guessed by inspection. We have more than one integrating factor for a non-exact differential equation. Sometimes integrating factor is easy to determine and sometimes it is quite difficult. For this, we have 4 rules to find out integrating factor for a given non-exact differential equation. So in this video, we will read about the 4 rules regarding integrating factors, and we will solve 3 examples on it. So be attentive, and it will help you a lot in your course. So looking to the screen, rules for the determination of integrating factor. This is our headline. Rules for the determination of integrating factor. What is integrating factor? Sometimes it is difficult to find the integrating factor by guessing or inspection. Thus we have the following rules. Rule number 1. This is rule number 1, and we read this rule and then we will use it for the solution of an example. What is the rule number 1? When the differential equation m dx plus n dy is equal to 0 is non-exact such that it is homogeneous differential equation and mx plus ny is not equal to 0, then we have the integrating factor 1 divided by mx plus ny. Here we have been told that in case of a homogeneous differential equation, which will be non-exact differential equation, we will find out mx plus ny is equal to mx plus ny. If this is non-zero, then reciprocal of this expression, that is 1 over mx plus ny, will be the required integrating factor. To know about the rule, let us solve an example. This is an example and we have to use this rule. Solve m dx plus n dy is equal to 0. This is a differential equation of the form m dx plus n dy is equal to 0. Here we have minus sign. We will take this minus sign into the bracket and we will convert this differential equation in the standard form. So by taking minus sign to the bracket, we will get this differential equation. Now it is in the form of m dx plus n dy is equal to 0. Equation 2 is of the form m dx plus n dy is equal to 0, where m is equal to x square y minus 2xy square and n is equal to 3x square y minus x cube. This is the differential equation in the given form. Now we have to check whether it is exact or non-exact. So differentiating m with respect to y. During this differentiation, we will operate y and will treat x as constant. So this y will become 1 and this y square will become 2y. Finally, we will get del m over del y is equal to x square minus 4xy. Now partially differentiating n with respect to x. During this differentiation, we will operate x and will treat y as constant. So this is the result. Now looking to the value of del m over del y and del n over del x, both are unequal. Hence this condition condition for a differential equation to be exact fails. Thus, the differential equation is not exact differential equation. Moreover, equation 2. This is equation 2, which is homogeneous differential equation. Now we have to here we came to know that the given differential equation is non-exact. Moreover, it is a homogeneous differential equation where m and n are homogeneous functions of the same degree, and that degree is 3. And that degree is 3, here degree is 3, here degree is 3, so degree of m is 3, here degree of this term is 3, degree of this term is 3, so degree of the function n is also 3. So the differential equation is homogeneous. Now we have to find out value of mx plus ny. We have to find out value of mx plus ny, putting the value of m and n and simplifying. Here we will get x square y square, which is not equal to 0. Since this is not equal to 0, so integrating factor will be equal to 1 over mx plus ny, and it will finally be equal to 1 over x square y square. Multiplying equation 2. This is equation 2. We have to multiply equation 2 by integrating factor 1 over x square y square. This is the multiplication. Now simplifying this equation, we will get m dx plus n dy is equal to 0. This is the new differential equation after multiplication by integrating factor. Now we have to check the condition for exactness, whether del m over del y is equal to del n over del x. Now we come to the next slide. This is the next slide. Here we have value of m, and we have to differentiate with respect to y. With respect to y differentiation, it will give minus 1 over y square. This 2 over x will become 0 because we have to treat it as constant. Similarly, n, this n is value of n is equal to this one. We have to differentiate with respect to x, so this x will become 1, and finally we will get minus 1 over y square. And x is, since x is y is constant, so 3 over y will be equal to 0. Now comparing both the values, we see that del m over del y is equal to del n over del x. Hence equation 3 is exact differential equation. Equation 3, what was equation 3? Equation 3 was that equation which was obtained by multiplying the integrating factor. So we have checked that new differential equation which satisfies condition for a differential equation to be exact. Since the new differential equation is exact, so we have the formula. The general solution is equal to integral m dx, where y will be constant, plus integral terms of n free of x into dy is equal to c. This is the formula to find out the general solution of any exact differential equation. The new equation was exact differential equation, so to find out the solution we will always use this formula, putting value of m. This is value of m, and now looking to n, we have to take that term from n which will be free of x. So this second term will be ignored and the first term will be taken. This 3 over y have been taken here. Now integrating all the terms, integral dx y is constant, so it has been taken out, and now integral of dx is equal to x. Integral of 1 over x dx is equal to log x. Integral of 1 over y is equal to log y of constant of integration. We can take any constant integration. Here we have taken it log c. Now simplifying, this is the simplification. The 2 will go to x, it will become log x square log y cube. Now finally writing this equation in this form, so finally we will get the general solution as x over y plus log of y cube over x square is equal to c. यहाँ पे here log y cube minus log x square will become log of y cube divided by x square. So finally this is the general solution of the differential equation, which was homogeneous but not exact differential equation. Here we have used rule number 1. Now we come to another rule, rule 2. This is rule 2. Read the statement. If the differential equation m dx plus n dy is equal to 0 is not exact differential equation and is of the form y f of xy dx plus x g of xy dy is equal to 0, such that mx minus ny is not equal to 0, then we have the integrating factor 1 over mx minus ny. If the differential equation is in this form, we will have a function f of xy into y dx plus function gxy x dy is equal to 0 whenever we have our differential equation of this form, such that if mx minus ny is not equal to 0 and that differential equation is non-exact, then to find out integrating factor we will take this formula. Integrating factor is equal to 1 over mx minus ny. This will be the integrating factor. This integrating factor will always be used when the differential equation is non-exact and whose form will be f of xy y dx plus g of xy x dy is equal to 0. Now we will solve our differential equation of this form. This is the differential equation. First of all, look to the structure, the shape of this differential equation. This bracket is a function of the form f of xy, and we have y dx. Y dx is here, and function is of the form of f of xy. Similarly, function g is also here, which is of the form g of xy, and into x dy is equal to 0. The shape of this third is of the form as discussed in rule number 2. Here m, this m is equal to y f of xy m, and this is n. Check del m over del y not equal to del n over del x. We have to pick out m from this differential equation. Similarly, we have to take n from this differential equation. We have to check this condition whether it is hold or not, and definitely it will not hold, but we must check this whether in case if it is non-exact, then we have to use rule number 2. If it is exact, then we have to solve directly. Now we come to the next slide. To mx minus ny, this is the denominator of integrating factor. We have to put the value and then we will check whether it is non-zero or not. So putting the value, this is value of m, this is part of m, this x is part of m, this is multiplication by x, and here multiplication by y. This x is this x and this y is this y. These two are by formula. Now simplifying, finally we will see this is the result, which is not equal to 0. So integrating factor will be equal to 1 over mx minus ny, and this is the integrating factor. This is the integrating factor. Multiplying differential equation by integrating factor. Now we have to multiply the given differential equation by this integrating factor. Here we see the multiplication, here this is the multiplication. Simplifying, we will divide first term by this integrating factor, similarly the second term by this integrating factor. So we get this differential equation. Multiplying by 2, we have to multiply both sides by 2, we get this differential equation. Now taking, it is of the form m dx plus n dy. Here m is equal to this one is m and this one is n. partially differentiate m with respect to y and partially differentiate n with respect to x. Partial differentiation of m with respect to y has been here del y. This y, looking to this bracket, here we have product of two functions, so we have to use product rule, and this 1 over x is constant, it will become 0. So product rule is first function derivative of tangent, which is secant square. Similarly, derivative of xy with respect to y will give us a x. From here we will get a x. So this x and this y will become xy. Secant square will be on the same position. Similarly, this function del y over del y plus 1 over del y of 1 over x, which is equal to 0. Looking again, here we have product of two function. So first function derivative of tangent, which is this one, or this is by chain rule, plus tangent or partial derivative of first function plus partial derivative of the last function. Now simplifying, this will be equal to 0, and we will get this result, and finally we will write this result as tangent xy plus xy secant square xy. Now we have to calculate del n over del x in the next slide. Then we will compare both the values, whether the condition for exact differential equation holds or not. Now we come to the next slide. Here we see partial differentiation of n with respect to x. To find out differentiation with respect to x, we will operate x and will treat y as constant. Since this is first function, this will be the second function because it involves x, so we will consider these two functions. X will be the first, tangent xy will be the second. We will use product rule of differentiation. This y will be equal to 0 because it is constant, while product rule of derivative of first function derivative of tangent, which is secant square, by chain rule derivative of xy. Now this is the tangent function is again here, and derivative of x or the partial derivative of the last function, this will be equal to 0 because y is constant and we have to differentiate with respect to x, so it will be equal to 0. This 0 is here. So this result, and writing in this form, comparing value of del m over del y and del n over del x, we see that both are equal. Thus the given equation is exact differential equation. The general solution is integral m dx, where y will be constant, plus integral term from n with no x dy is equal to c. Putting the value of this it is the value for m, and now look, this is value of n. Looking this one, this is value of n. We have to take that value, that term which is free of x. This term have x, so we will omit it. This term is without x, so we will take this term and will put here minus x beta y. Now tangent means sine over cos, integral of 1 over x, integral of 1 over y. C is the constant of integration, where we can take it log c. Derivative, here we have f dash, this is f, denominator is f, numerator is f dash, so log denominator. Derivative of cos is minus sine. Derivative of xy with respect to x is minus y. Here denominator we have f dash, so we will use formula log denominator. Here log denominator, here again log denominator, log c. Now simplifying, so this is the result of this log of something plus log of another function minus log of third function. So we can write in this way. Here we have log of a plus log of b minus log of c. So writing in this way is equal to log c. Cancelling log, this log will be cancelled with this log, this, and finally simplifying the result, this will be the answer. This is the required general solution. rule 3. Now we have to read rule 3. Rule 3 whose statement is, if the differential equation m dx plus n dy is equal to 0 is not exact differential equation, and if del m over del y minus del n over del x divided by n. In the previous video we have shown this rule as del m over del y minus del n over del x divided by m is equal to f of x. F of x is function of x alone, then integrating factor will be equal to integral f of x dx. This f of x will be used to find out integrating factor. Integrating factor will be equal to this one. So if the differential equation is non-exact and if value of this expression is a function of x alone, then we will find integrating factor by using e raised to power integral px dx. This is rule number 3. Case rule number 4. If the differential equation m dx plus n dy is equal to 0 is non over del x minus del m over del y divided by m is equal to g of y, which is function of y alone, then integrating factor will be this one. This is the differential equation. Read the look to the two rules. If this expression gives us function of x alone, then we will take this formula for integrating factor. If value of this is function of y alone, then we will take this formula for integrating factor. Now we have to check the below example whether we should use rule number 3 or rule number 4. So looking to the example, this is the differential equation given m. What is m? M is equal to y. Del m over del y will be equal to 1. Now taking n, this minus will go inside and we will get n is equal to minus y plus 3x plus 3. Del n over del x will be equal to 3. Since both the values are unequal, hence the differential equation is non-exact. In both the rules, the differential equation is non-exact. Integrating factor is always needed when the differential equation is non-exact. So we checked that the differential is non-exact. Now we have to take this expression. Taking that expression and putting the value, we get minus 2 divided by 3x minus y plus 3. Since here we did not get a function of x or y alone, so we will ignore this result. Here looking to this one, here we did not find a function of x or y alone, so we will not take this. Moreover, now taking the other expression, here we have two expressions. This is first expression, this is another expression. Now taking this expression, this is the expression putting the value which gives 2 over y, which is function of y alone. Hence we will take this result to find out integrating factor. Integrating factor is equal to e raised to power integral gy dy, putting the value e raised to power 2 log y, which will be equal to e raised to power log y square, cancelling these two. Remember, whenever these two functions comes together, they will cancel each other. We will get y square. Now we come to the next slide. Here rule number 3 and rule number 4, we took rule number 3, but that rule is not applicable. Hence we took rule number 4, which is applicable here, and now we are on the way towards our solution. Multiplying 1 by y square. This y square was the result of integrating factor. This was the integrating factor by rule 4. Multiplying the differential equation by y square, and we will get this differential equation. This minus will go inside, so the y cube, this y cube is value of m and this will be its partial derivative. This n is valued here, value of n is given, whose partial derivative with respect to x is also here. Now comparing both the value, this value and this value are the same, value of partial derivatives are the same, hence del m over del y is equal to del n over del x, and equation 2 is exact now. Equation 2 is exact now. This is the new differential equation obtained by multiplying with the integrating factor. Since the new equation is exact, and thus we will use this formula to find out the general solution. Integral m dx, where y will be constant, plus integral terms of n with no x dy is equal to c. Here we have is equal to c. This is equal to c y cube. This y cube, and similarly y cube is here. So y cube, now looking to n, here we have to take that term which is free of x. We will take y square, we will not take this term. Similarly we will take these two terms will be taken here, and we will proceed towards the solution. Integral of y cube with respect to x, y cube is constant, so it will be here. Integral dx will be x. Integral of 3y square will become 3y cube over 3. Integral of y cube will be equal to y4 over 4 is equal to c. Simplifying, now multiplying both sides by 4, this is the simplification. Replace 4c by a, and finally this is the general solution of the non-exact differential equation, for which we used rule number 4. Thank you.